Hey, Hers, and welcome to Energy from Fuels. This is just a NAT 5 revision. So we're going to start enthalpy of combustion, which is a higher topic. We're going to start that on Friday, but we're just going to do a quick wee revision of the NAT 5 just so we're up to speed with it. You might want to pause the video so that you can copy down the questions. I'm just going to go straight into the answer. So question 1. 25 grams of ethanol was burned. The energy released was used to heat 250 centimetre cubed of water from 22 degrees Celsius to 40 degrees Celsius. Calculate the energy released. Okay, so this is a simple EH equals CM delta T calculation. We put our values at the side. So we're trying to calculate the energy released, so we don't know that, so we put a wee question mark. Okay. The specific heat capacity, it doesn't say it in the question, however, we are using water, and you should know off by heart that the specific heat capacity is 4.18, yeah, kilojoules per kilogram per degree Celsius. This is an important one, that there is the mass of water. Okay, now we've got two masses here. We've got the mass of ethanol. We've got the mass of ethanol and we've got the mass of water. Okay, so we don't use that 25 grams. Yeah, that will come into it when we start doing the higher work. Okay, so we for the NAT 5 we only focus on the mass of water. It's 250 centimetre cubed, and remember we need to divide that by 1,000 in order to get it into kilograms, so that's 0.25 kilograms. The change in temperature, it went from 22 degrees Celsius to 40 degrees Celsius, so that is 18 degrees Celsius. And if we just, well, all we need to do is sub all those numbers in, so 4.18 times 0.25 times 18, and if I just do this on my calculator very quickly, we get 18.81 kilojoules. Yeah. Right. Question 2, a wee bit harder, but in the same regard, it's relatively straightforward. So 40 kilojoules of energy released when 8.4 grams of pent-1-ene was burned, that should say. This energy was used to heat up 125 centimetre cubed of water. Calculate the change in temperature, and from this, the final temperature if the water started at 20 degrees Celsius. Okay, so the question is asking us to find the change in temperature. Okay, so that is delta T. Now remember, there's many ways you can do this. You can use the triangle, or probably maybe the easiest way is you put EH on the top, and then anything that isn't delta T you put on the bottom, so that's EH divided by CM. Okay, do our wee sidebar. So delta T is what we're trying to find out, so we don't know that. Yeah, the energy is 40 kilojoules. Okay, again it is water we're heating up, so the specific heat capacity is 4.18 kilojoules per kilogram per degree Celsius. The mass, again we've got two masses. We've got the mass of pent-1-ene, and we've got the mass of we've got the mass of pent-1-ene and we've got the mass of water. Again, we don't use the mass of pent-1-ene, we use the mass of water, so that's 125 centimetre cubed. Divide that by 1,000, 0.125 kilograms, and then all you have to do is sub that in, and there you go, easy. Now, if you were in my class during NAT 5, I always told you to do the bottom calculation first, because if you put 40 divided by 4.18 times 0.125, it doesn't give you the right answer because the rules of BODMAS, etc., it doesn't work. So you need to do the bottom sum first. So that would be 40 divided by 0.5225. So 40 divided by that, you're getting 76.6 degrees Celsius. Okay, so that is the change in temperature. Now, we're not finished there, because the question said calculate the change in temperature, and from this, the final temperature if the water started at 20. Okay, so if the water started at 20 degrees Celsius and it changed by 76.6 degrees Celsius, our final temperature has to be 96.6 degrees Celsius. And there you go. Okay. Right. Another type of question you can get. Again, you might want to pause the video, write out the question, draw the wee diagram. You've all recognised this wee diagram. This is the experiment that we did. That's the wee heat shield, the fuel, and that's the copper can with water in it. So why are the experimental values much lower than the actual values? So you'll, if we did this in the lab, the values that we got for each fuel would be a lot lower than the values that we could find in the data booklet. So why is that? And there's three reasons for that. Now the first one, okay, so there's three explanations. Now the first one is that heat could be lost to surroundings. Okay, so what we mean by that, when the fuel is burned, instead of all of the energy going into heating up the water, what can happen is some energy can be lost. Yeah, so that's why the value is a wee bit lower. Now another one is incomplete combustion could take place. And again, from that 5, incomplete combustion just means that we've burned it in a limited supply of oxygen. Okay, so incomplete combustion could take place. So we need to make sure we've got a plentiful supply of oxygen when we do these experiments. And the third one, the can, now it's usually a copper can, but obviously it doesn't have to be. The can could absorb energy. Okay, so instead of the energy going into the water, it gets absorbed by the can instead. Now, when you come to hire, the two ones I would always say are these two. Okay, so the heat could be lost to surroundings, or incomplete combustion could take place. That's the two you want to make sure you're saying. This one can get a wee bit complicated. I'll go into it when we go into hire, but these two here I would always go for. Now, last wee bit, and then that is us. It is a short video. There are solutions. Okay, the solution in order to get more of the energy into that water. There's a couple of things we could do. Okay, we can use, like we have in this diagram here, we can use a heat shield. Okay, and what does that do? Prevents energy lost to surroundings. Okay, but you guys have all seen a heat shield. Even from this diagram, you can see that the energy can escape. Yeah, from the front part as well, it can come out. So a better solution, and a solution that we use in order to get the actual values from the data booklet, is we use something called a BOM just getting the right spelling. We can use a BOM calorimeter. Okay, now you don't need to know what that is. I'm going to go into a wee bit more detail when we do the higher part. Okay, I'll show you a wee diagram of it. I'll show you a video perhaps of how a BOM calorimeter works. But basically what that does, it ensures no heat loss to surroundings, and it ensures complete combustion. And the reason it does that is because oxygen gets pumped into the BOM calorimeter. Okay, so that's all you guys really, apart from this wee bit here, you should already know. Yeah, this wee bit, we're just introducing it to the higher topic. What I'm going to do now, I'm going to post up questions on Teams. I'll give you the answers and you can self-mark your own questions. Okay, right, thank you.